Now that we got code blocks installed, let's see how we can debug your program with code blocks. So this is assuming that you already watched the last video and installed code blocks on Windows or Linux, and you have GCC and GDB and everything installed and set up. So let's start. So programming without debugger is like driving without a car without knowing how to use the brakes. Whenever there is a problem, you just brake. That means stop and see what's wrong with the source code. You can actually see the variable values. It's much easier than guessing what is wrong by staring at the whole source code printout. So that's debugging. Also allows you to look at somebody else's code and stop and see, okay, what are they trying to do, without actually having to know everything else in their code. And that's the way it works in the industry. So debugging is an essential part of coding, and language without debugger are basically toy languages. How do you debug? First of all, when you compile, you turn on GCC -fault to fix all the warnings, so that basically any errors that are there are something that is a real logical error, not something that's trivial and that the compiler can warn you about. Second is that you add assertions. You include #include assert.h and then say what are you expecting it to be. You just assert that value. So it's assert g equal to 1 in this case. That means in the debug mode, the program will actually check that g is equal to 1, and if g is not 1, it will stop and say, hey, like you have a logic error. And then before g, you're computing g is a GCD of 37. So we're going to use the latest code blocks, which version is there right now, and you're not going to use obsolete compilers or IDEs like Turbo C or Dev C++, and they are gone, and code blocks is free and it's pretty good right now. Let's look at a program. So you type the following program into code block called main.cpp, and then you have a for loop I equal to 0 to 5 and print out I into I 5 times and return 0. And first thing you can do is click on in the left column and you get a red dot. Red dot means there's a breakpoint, and a breakpoint means it will stop out there, and then the program, when you run it, will stop at this point, and you can see what is happening at that point, what is the value of I. In this case there is no error, but sometimes there will be an error and you can stop anywhere in the code by putting a breakpoint, and we will go to look at more details as we go along. First you build the program also, then you build the program. It says building, compiling, executable p16.exe and 913 kilobytes and 0 errors, 0 warnings in 2 seconds. Then you're going to the thing you can do is you can watch variables. So you say debug edit watches, debug edit watches, and a lot of options out here in debug. You need to know all of them, and they all will come in use. You can't really learn it when you need them, you just need to know beforehand. So what is a watch? So you want to watch a value of I. You say in the edit debugger values, edit debugger watches, you say add, the add button, then you type I, you get this pop-up in which enter the new watch keyword. So you want to see the value of I, to type in I and say okay. So during debugging it will show you the value of I instead of having to type in every time. Then you just start debugging. So you can start debugging by stepping into or run to cursor, and then you can attach it to the sensor. We'll look at it later on. And then there are a lot more options out here. And then when the program starts running, it will stop at the breakpoint. There will be a yellow arrow pointing to the current statement. And then if the watch window is not available, you can right click and select the panes that are available. So panes are breakpoints, call stack, CPU registers, disassembly, memory dump, running threads, and watches. So in this case we are interested in watches. So here is doing STL vectors and stuff. We don't care about that. Setting breakpoint. Every time you do something, it shows you in the debugger log what is a GDB command. So you could actually run the UI without the UI also from the command line by typing GDB commands. So it's a good place to see how the IDE is converting your clicks to GDB commands. So and the stopped at documents main.cpp line 5. That's where you put a breakpoint. Okay. Then then there are many options out there. So one is that after you stop at a breakpoint, you see the value of I is 0 at this point. Local variable I is 0. Function argument is arguments are there. I equal to 0 it says. You can go to the next line by pressing F7. You can go to the next instruction in assembly. You can step into a function. You can step out of a function using Shift F7, Shift Control F7. You can turn the breakpoints on and off, or you can just run continue till you reach the cursor again. And how does it do that? It puts a temporary breakpoint, and so it will run, and then when it reaches the current code, it will stop, and debugger will transparently remove the breakpoint. And the more complex ways of doing stuff, debugging, and you keep stepping to the code till I equal to 4 appears. Then I eventually press few more times F7 to go, and I equal to 5 will appear in the watch window. And you can press Alt F7 to see the assembly code. So you can see the assembly code, disassembly code, and it takes the object code and disassembles it. And if you have debugging symbols, it will also put in the variable names out there. So for example, it's saying main, call main out here, and you need to make a small program like this and debug it yourself to get an idea what kind of assembly you are expecting. And then when you're done with debugging, you found a problem and you fix, you can just say stop debugger. And these are the commands, and then these are the shortcut keys. And you can show the smaller windows like call stack, breakpoints, disassembly, examine memory, the number of threads. We are right now running a single thread program. A console program is single threaded, but you could have a multi-threaded program also, like GUI programs. And then CPU registers. So you have EAX, which is a main register, extended A register, 32-bit register, and then ECX the counter register, DX is the destination register, BX is the base register, ESP is the stack pointer. And eventually you'll learn how to. So we have all these windows to look at, and then there are advanced breakpoints. If you're really hard to find a bug, we have to use advanced breakpoints. What are advanced breakpoints? Suppose you have a program like this, main with something in a local variable I equal to 2 F21, array of size 21. Then you call G. G is another function with I equal to 2 and F equal to array. And then main calls G. G takes a integer I and a pointer to a array F. Then while I is less than 10, you fill in some I into 2 minus I into 2 plus 1 and increment the array. So this is kind of a complex function. It's writing into memory, and you're not sure where it's going to write into. So now what will happen when you try to debug and run? It will crash, and this is called as smash the stack. Basically, this F is pointing to a wrong location minus, so it overrode some part of the stack, return value, and then everything got trashed, and you can't really see what happened. And this kind of crash is very hard to debug because you lost all your context, and so debugger stops, but then it's just a big bunch of random data because your stack and the return values are where you came from, what the function name is, everything got deleted by the overwriting in this F++. So what do? We have to do some advanced breakpoints. So what is advanced? So what kind of advanced breakpoints we have? And this is a conditional breakpoint. So in this case, what you have to do is you have to edit a breakpoint. You set a breakpoint, edit a breakpoint, and then you want to say when do you want to break. So what it says is a breakpoint, edit breakpoint, and you say break when I is minus I into 2 less than 0, or this expression that we are writing into is less than 0 or is greater than 21. So you want to see when you are going array out of bounds. In this case, the array is on the stack. So the expression, this expression is true, the debugger will stop. Then you say run until breakpoint is triggered. Run, and then what happens? Select the expression, say view in basically, and then you run it. So what happens out here? At this point, it will run and then it will stop at some point. Then you can look at the values what I is. So it says I equal to 3. So what you go down and see, and you find that the I basically expression is wrong. So you fix that. Okay. So in this case, you are editing a breakpoint, but expression is evaluated symbolically. It's not really in machine, so it's really slow. So if you really want to have a faster breakpoint, which is this will be a million times slower than the real code, because the debugger is actually evaluating the expression every time you hit the breakpoint. It's not really in the code. And second type breakpoint is available in the CPU itself. It's called a data breakpoint, a hardware breakpoint. And then hardware breakpoints are basically you tell the CPU, hey, I want to stop when this memory location is overwritten or read. So you can have the Intel CPU provides 3 breakpoints: break on read, break on write, or break on read or write. So you want to say, I want to enable, I want to say data breakpoint F21, I want to stop when F21 is written on. So that's a location you don't want to write into. So then you run it. It will run really. In this case, it's a really small example. It doesn't matter. But if you had like really huge code, it would matter. The speed would matter, and it also lets you catch things when somebody is writing into array, but you don't know who's writing, which point of the code. You can put a breakpoint, read or write breakpoint to see how your code is getting used by somebody else in a large amount of functions. So then it will stop at this point. You can see who's writing into the wrong value, into the wrong place, and then fix it. So the second thing is that code block actually calls into GDB commands. So you can see if you enable GDB log window, you can see the GDB commands generated by your GUI actions. So breakpoint is one, and then condition is set like this, and you want to print output of this thing, and then you're adding a watch, hardware access read write breakpoint, a watch it's called. So what are the debugging tips? So basically these are things. If your program caches an input, save the input, hardcode the data causing the problem, and then run it, put it in a batch file and run it as many times as you want, and so the debugging is easy. You may want to run them like 100 times before you actually figure out which part of the code you want to fix. Second thing you can do is use binary search to put breakpoints before and after the crash, around the crash, to see how far does it run before it actually goes bad. And then when you're in trouble, the code looks having some problem, hairy code, what you do is basically step over the things and watch the variables and see that they are as you expect. There's something amiss, you basically know that the code is wrong, and then make a test case and learn how to write unit tests. So basically save the code and write a unit test so that next time you hit something, you're able to run the test to make sure that okay, your code changes are not crashing the thing again. And third thing is use CVS if you are on a single user to save, or JIT if you are on a network to save, even on a single server, to save copies of your code. Every time there's a problem, you can go back to older version and compare what changed and what was the last time you ran without a problem, and find in the time sequence where the problem occurred. So, and if it's a really hard problem, you have to use Valgrind or Purify. Those are memory debuggers, and if they spot memory leaks and memory overrides or array out of bounds reads or write. And then save whatever you do, make notes in a file and put comments explaining the problem, so that next time you hit it, you know where to look for, or somebody else looks at it. And put comments in your code, and if the comments are like assertions, convert them to code. Instead of saying hey, we expect x to be 1, you just say assert x equal to 1. And sometimes you get weird error messages. You just type into Google, you'll find what other people did, and usually you'll find that it's a common problem in the beginning, but eventually you'll hit harder and harder problems. So let's see how this is another tip. So whatever is the comment, t is a sum total. So first thing is, instead of putting it t as a sum total as a comment, you just convert it into a variable name your variables properly, total sum, so that by reading the user knows exactly what the variable is, instead of having to guess t is total sum. Then instead of saying assume x is greater than 0, you just say assert x is greater than 0. So then debug mode, it will actually check that x is greater than 0. And third thing is, the third tip is keep it short. Don't add extra code. X greater than return 1 0. It can actually be returned total sum greater than 0. So code becomes smaller, clearer, and comments usually go wrong with time when people change their code, but don't keep that comments up to date. Okay, so that's about debugging, and then we look at other stuff later.